Today we'll be talking about volcanic eruptions and some of the hazards that result from them. There are two main types of volcanoes. Shield volcanoes are gently sloping and built over time by low viscosity lava flows. One high-profile volcano of this type is Kilauea. Composite volcanoes are cone-shaped structures made by thicker, more viscous magma. Because of this viscosity, gases tend to get trapped in the molten rock. Eventually, this leads to an explosive eruption as high pressures overcome the magma's resistance to flow. Examples of composite volcanoes are Mount St. Helens and Mount Rainier, seen here. So what would it look like if Mount Rainier erupted? Despite popular belief, lava would not be the most direct threat from the eruption of a composite volcano. Lahars, or mudslides triggered by the eruption, could travel far enough to reach the city of Tacoma, which would cause serious damage. Meanwhile, composite eruptions will likely generate pyroclastic flows. Pyroclastic flows are the result of lava being propelled into the air by hot, high-pressure gas. The lava quickly solidifies as it rises. The end result is a mixture of rocks, glass, and hot gas raining down on the surrounding area as the cloud flows toward the ground. A more lingering effect of the eruption would be ash clouds, which will be transported away from the mountain by atmospheric currents. We ran a high-split trajectory volcanic ash forecast model. A high-split model tracks movement of air parcels, or large bubbles of air, and how they disperse given particular atmospheric conditions present at the time that it is run. This model is projected over a 48-hour period using the 6Z GFS model at 1 degree resolution, initialized on April 14, 2017, with the eruption beginning on April 20, 2017. Each image represents a time period of 12 hours and demonstrates the dispersion of the ash plume across the western United States during this period. If we assume a brief, intense eruption with an ash plume upwards of 80,000 feet high, within 48 hours the volcanic ash plume would be dispersed over a region ranging from southern Canada to the Mexican border. The winds that primarily impact the movement of the ash clouds are those in the upper levels of the troposphere. Below that level, heavier particulates will quickly fall out and be deposited. The GFS model we used in our high-split simulation can easily explain the ash clouds movement. When the volcanic eruption initially occurs, there is a relatively weak southwesterly flow at 10 kilometers, which is close to the top of the troposphere. As a result, the ash cloud will slowly move off to the northeast and disperse over the Canadian Rockies. One day after the eruption, an upper-level high-pressure area is forecast to move east into the region. An area of stronger winds moving around the upper-level high will impart northwesterly flow. As a result, the ash cloud will likely be spread throughout the mountain west of the United States within a day or two of the eruption. With this in mind, there are considerable impacts across the western United States with regards to visibility, aviation, and temperatures. Visibility in the immediate vicinity of the eruption would be significantly reduced due to falling ash, which creates hazards for aviation. Aviation is also significantly impacted by the ash itself, as it can cause jet engines to fail. In addition, ash clouds can lower the temperature of the area by reflecting incoming solar radiation. On a big enough scale, this can have repercussions for agriculture, but probably would not result from the eruption of the scale we modeled. Finally, the ash poses a health risk as inhalation of volcanic ash can cause respiratory problems. An eruption from Mount Rainier can cause many hazards such as lahars, pyroclastic flows, and ash clouds. As with other composite volcano eruptions, the severity and distribution of these effects vary.